Picture the most violent event in the known universe. A star, something 20 times heavier than our own sun, running out of fuel after millions of years of furious burning. Its core, no longer able to support the crushing weight of everything above it, collapses in less than a quarter of a second. The outer layers come crashing inward at a quarter the speed of light, hit the collapsing core, and bounce back outward in an explosion so catastrophic it briefly outshines the entire galaxy it lives in. Billions of stars, outshone by one dying one. That is a supernova. And what it leaves behind, the collapsed core, the crushed remnant of a star, is called a neutron star. A city-sized object so dense that a single teaspoon of its material would weigh about 1 billion tons on Earth. We thought we had neutron stars figured out. We thought they were extreme, yes, but understood, catalogued, explained. We were embarrassed to be that wrong, because in 2017, a single detection from an observatory that wasn't even looking at the sky changed everything. And what it found hiding inside that dead star has forced physicists to confront a question they have been avoiding for nearly a century. What actually happens to matter when you compress it beyond any limit nature was ever supposed to allow? Let's back up, because the strangeness of neutron stars is worth sitting with before we get to the part that breaks everything. When a massive star collapses, the core gets squeezed to extraordinary densities. Electrons and protons are crushed together into neutrons. The entire remnant, often containing more mass than our sun, is compressed into a sphere roughly 20 kilometers across. 20 kilometers. You could drive that in about 15 minutes on a highway. But inside that sphere, the density reaches levels that are genuinely incomprehensible. The matter packed into a neutron star is not like any matter you have ever encountered. It is not solid in the way rock is solid, or liquid in the way water is liquid. It exists in states that have no analogy in everyday experience. Near the surface, it behaves something like an incredibly dense crystal lattice of neutrons and atomic nuclei. But deeper in, under pressures that eclipse anything achievable in any laboratory on Earth, the matter begins to do things that our best physics can only approximate and argue about. For decades, the debate at the center of neutron star physics has been about what lives in the core. The extreme pressure deep inside these objects may be sufficient to dissolve neutrons themselves. Neutrons are not fundamental particles. They are made of quarks, held together by the strong nuclear force. Under enough pressure, the theory goes, neutrons can no longer maintain their individual identity. They dissolve, and the quarks flow freely, forming something called quark matter. A state of matter that has never been observed in any laboratory anywhere. A state of matter that, until recently, lived entirely in the domain of theoretical physics. The problem is that for decades, we had no way to test whether it actually existed inside neutron stars. We couldn't crack one open. We couldn't take a sample. We could only observe them from thousands of light years away and argue about the math. Then, on August 17, 2017, a signal arrived at the LIGO and Virgo gravitational wave detectors. Not from a single exploding star, but from two neutron stars spiraling into each other in a death dance that had lasted hundreds of millions of years and was now ending in a catastrophic merger. The event was labeled GW 817. It was the first time in history that gravitational waves and light were detected simultaneously from the same event. Observatories around the world pivoted to watch. It was, in the words of one astrophysicist, the most observed event in the history of astronomy. And the data it returned was extraordinary. Gravitational waves are ripples in the fabric of space-time, and when two neutron stars spiral together, the waves they produce carry information about the stars themselves. Specifically, they carry information about how the stars deform as the gravity of each one pulls on the other. A neutron star made of conventional nuclear matter deforms differently than one containing exotic matter. The way it stretches and distorts, a quantity physicists call tidal deformability, is encoded in the gravitational wave signal like a fingerprint. And when the LIGO and Virgo teams analyzed the waveform from GW 17081 unseen with exquisite precision, they got a measurement of that deformability. Then they compared it to theoretical predictions for different types of matter. The result narrowed down, dramatically, what the interior of a neutron star could possibly be made of. It ruled out the softest equations of state, the models that allowed the most exotic, most compressible types of matter. It also ruled out the stiffest ones. It carved out a range. And right in the middle of that range, sitting uncomfortably but undeniably, were models that allowed for a core of quark matter. Not confirmed, but not excluded. Disturbingly, tantalizingly possible. And then the measurements from a different instrument pushed things further. NASA's NICER telescope, mounted on the International Space Station, was designed to do one specific thing with extraordinary precision. It measures the X-ray pulses from spinning neutron stars called pulsars, with timing accurate enough to determine both the mass and the radius of the star to an unprecedented degree. Because here is the thing about neutron stars. If you know the mass and the radius simultaneously, you can constrain what the interior must be made of. Different compositions produce different sizes. A neutron star made purely of conventional neutron matter at a given mass will be a slightly different size than one with a quark matter core. The difference is only a few kilometers. But NICER can measure it. And what NICER found, particularly in its measurements of the pulsar J0740+66 one of the most massive neutron stars ever measured at around 2.1 times the mass of our Sun, pointed toward a star that was simultaneously very massive and unexpectedly compact. That combination, high mass and relatively small radius, is precisely what theoretical models predict for a neutron star harboring a core of quark matter. Conventional matter alone struggles to reproduce it. Now here is why this matters beyond the already staggering fact of exotic matter inside dead stars. If quark matter exists inside neutron stars, it would represent the only place in the observable universe today where the conditions of the very early universe are being recreated. In the first microseconds after the Big Bang, before the universe had cooled enough for quarks to bind together into protons and neutrons, all matter existed in a state called a quark-gluon plasma, a hot, dense soup of free quarks and gluons filling all of space. That state lasted for only a fraction of a second before the expanding, cooling universe caused quarks to permanently confine themselves into the particles we know today. It has never existed again anywhere in the cosmos, except, potentially right now, inside the cores of the most massive neutron stars, where pressure replaces temperature as the mechanism that frees quarks from their confinement. These objects may be the only places in the entire present-day universe where matter exists in the same fundamental state it did at the dawn of time, sitting quietly in the darkness, spinning hundreds of times per second, waiting for us to figure out what they are. The implications cascade outward in every direction. Equation of state of dense matter, the relationship between pressure and density at these extremes, feeds directly into our understanding of how massive neutron stars can become before collapsing further into black holes. It determines the maximum mass a neutron star can reach. It shapes what happens in the aftermath of neutron star mergers, the very events that forge and scatter heavy elements like gold, platinum, and uranium across the cosmos. Every piece of gold in every piece of jewelry on Earth was forged in an event like GW 17081 unseen. The physics of the matter inside those merging stars determined how much gold was made, how it was distributed, how it eventually ended up in the cloud of gas and dust that became our solar system. The exotic matter debate is not an abstract argument between theorists. It is a question about the material history of everything, and we are closer to answering it than we have ever been. The LIGO detector network is currently running its fourth observing run, and the upgraded sensitivity is capturing neutron star merger signals that were previously too faint to detect. NICER continues collecting pulsar measurements, steadily tightening the constraints on mass and radius for more and more objects. A proposed next-generation gravitational wave observatory called the Einstein Telescope would be sensitive enough to extract detailed internal structure information from neutron star mergers across cosmic distances. The era of multi-messenger astronomy, combining gravitational waves, X-rays, radio waves, and optical light to triangulate the truth about these objects, has barely begun. We built particle accelerators the size of cities to smash protons together and briefly recreate the conditions of the early universe. We have spent billions of dollars and decades of effort chasing quark matter in laboratories on Earth. And the whole time, there have been objects sitting in the galaxy that may have had it all along. Dead stars, city-sized, spinning in the dark, and more exotic, more ancient, and more fundamental than almost anything else in the observable universe. We thought we knew what they were. We are only now beginning to understand that we never did. And that's it from this video. See you in the next one.